Okay, it's recording. Go to here. Go to here. Okay, so the first thing I want to do is I want to give you your quiz. Remember, you have a quiz every day in class. Don't worry, this is an easy one. It's over the syllabus and introduction, but we're still having people, we're still having people come into the class, right? Like getting registered for the class. So this will basically be a participation grade. But the first thing we'll do is the quiz will be on paper, right? But normally, though, your quizzes will be on Blackboard, and you'll have to use a laptop computer to do it. If you don't have a laptop computer, I will provide you with a laptop computer to do it on, and you can use that laptop during the entire class period. So raise your hand if you don't have a personal laptop computer that you can use in class. Does anybody need one? Because I can get it for next Monday. Huh? Oh, we can help you with that. Okay. So everybody here has a laptop computer they can use during class, right? Anybody need a laptop? Are we sure about this? You will not be able to take the quiz if you don't have a laptop. Okay? I would prefer that you use your own, but if you don't have your own, I can provide it for you. I had somebody in my other class that actually didn't have a laptop because they did their entire online for the last 2 years on their phone. So, and I said, how did you answer questions? How did you do a test? Does Proctorio or Respondus work on that stuff? So it was very unusual. Okay. So Sydney is there. Oh, so Kate's the only one that's missing. I thought Sydney was missing. I'm sorry. I apologize. So Kate's missing. All right. So here's your quiz. Generally, you will be able to use your notes on your quiz, but literally this quiz is about the syllabus and about me. So it's just my way of taking a roll, taking attendance, and it's completion right now because we still have people enrolling in the class. Did I not count you? God, that's terrible. I'm Asian, so I'm hard at math. 4. Two more. Come on now, why are you sticking? It's a super easy quiz. 2. 2. And 3. Because there's 7 of you there. And then you get 1 too. And like I said, you weren't there on Monday, but that's okay. Just do your best. All right, you have 10 minutes starting now. And then after the quiz, we'll sort our new student into their house. Caitlin won't be here until Monday, so we'll put that away. When you're done with your quiz, just bring them all together at your house table and give them to me. Well, that's so weird. It's blue on the screen. It's purple on the other screen. I swear, if any of you put on there that my favorite food is fish, I'll be really upset. Because I hate fish. Everybody finished over here? Not yet? Okay. You still got 10 minutes. Still got 5 minutes. Still working over there. still working over here. You done? Oh, what house am I in? It's on my mask. I'm wearing my Hufflepuff mask today to support my house. So. Yeah. Yes, please. Yes, please. All right. You guys done? Cool. Thank you very much. All right. Before we get started today, I would like to sort our new student into her house. Our new student is Natalia. Why don't you come up? And since we're all here, we should clap when she gets sorted, okay? So all you have to do is come up here. The sorting hat will choose for you, but all you have to do is tap the wheel. And then when you're ready, stop the wheel. Okay, Slytherin. Let's see here. Let's make sure you can be a Slytherin first. Yes! Slytherin! Yay! So when you sit back down at your desk, I want you to write your major on the front and what you want to be when you grow up on the front, okay? And the Slytherins are over there. For you people with 7 people in your groups, you might have to add another table. Yeah. There you go. Oh, dang, I forgot to give you the thing about the poem. That's all right, I'll give it to you later. She's got to write a poem, too. Oh, sorry, did I miss you guys? I totally missed you guys. Shows you how important this quiz is, right? It is hot in here, isn't it? Oh, I was sweating last time. All right. We all good? Let's get started with lecture today. And then I guess section 41 has lab today too this afternoon, okay? All right. So the first thing I want to talk about is that there was somebody in my other class who wanted to make the house competition a thing where if you earn points as you're answering the participation questions, the house with the highest amount of points gets extra bonus points at the end of the semester added to their points for their grade, for their class grade. So I said I would let everybody vote. So that's what we're doing now. Everybody scan the barcode. Everybody scan the QR code. The question is, do you want a house points competition for lecture participation questions? How do you want to implement that competition? No, I don't want the houses to compete. I love all my classmates. Yes, I do want to compete, but only the house that has the most points gets points at the end of the semester. Or, yes, I want the houses to compete, but all houses get points based on their standing. Okay? And let's see what the results are while you guys are doing that. I really should have logged in already if I forgot. Now, I'm not sure what I'm going to do yet, but I want to get your input to see what you guys think. I'm logging on right now to see what the answers are, or the responses are. So we should have in total, 27 students in the class. 2 are missing, so there should be 25 responses. Anybody having problems getting in? Anybody have problems getting in? No? Oh, awesome. Last time we had problems, remember? That's good news. That's great news. Okay, sorry. House points vote. There it is. Okay, overwhelmingly, everybody wants the third option, right? Which is we do the competition and all the houses get points based on their standing. Okay, so I will take that into account during my decision. I want to do that, but I need to make sure that it's okay with my boss, and we'll be good. So, is everybody happy with that if we do that? All the houses get extra points based on your standing? Okay. That means then that when you're answering questions, right, work hard to get these answers right when we're doing the questions. Okay? All right. Let's go ahead and get started. Today is going to be a pretty easy lecture. It's actually going to be kind of fun too. So I didn't realize how much science I didn't know. That makes you feel so reassured, doesn't it? No, it's things that you don't really get taught for a while. So let's just talk about the sciences real quick, right? The sciences. Um, the sciences are separated in two different sciences. We have the social sciences and we have the natural sciences, right? The social sciences are things like psychology, social science, political science, things like that. The natural sciences is what we're doing right now. And specifically, we're doing physical sciences. This chart is in your notes, so you don't have to draw it. The ones that I provided to you. Okay? So specifically, we are doing the physical sciences, and the physical sciences, of course, include physics, chemistry, astronomy, meteorology, and the one that I'm kind of about, geology, right? And then, of course, biological sciences is like, biology, zoology, molecular biology, virology, immunology, those kinds of things, all those ologies, right? So we'll be focusing mostly on the physical sciences today, okay? Mostly on the physical sciences. That being said, to do science, you have to do it with the scientific method. Okay? You have to do it with the scientific method. So measurements are the basis of all scientific research and investigation. And so to do that, right, to do scientific research, you first have to have some kind of observation of some kind of a problem, right? Then you come up with a hypothesis about that problem that explains that problem, okay? You want to explain the problem, you want to be able to try to solve that problem, and you have some kind of hypothesis that solves that problem. Well, how do you know that your hypothesis is correct? Well, you develop an experiment, right? You develop an experiment, and you test your hypothesis to see if you're correct. So I gave this example when we were in lab on Monday, but I'll give it again. Back when I was in school, they used to have this really greasy piece of chicken fried steak at the cafeteria, right? Really greasy. And I was like, man, is this thing like really fattening or high calories or something like that? So that was my question. So the experiment, my hypothesis is yes, it is, right? High calories. So how would I test that? Well, there's an instrument, a device called a calorimeter that you can put food into, or anything you want really, wood, food, anything, a Cheeto, put it in there, and then it lights it on fire, right? And it makes the temperature of water or surrounding it go up. And as it goes up, you can use a formula to see what the temperature of the water is and then how many calories it has in it, right? Turns out I was right. Chicken fried steak is super fatty, super high calorie, right? Especially from this place. It was really greasy, right? So that's your experiment section. Once you've tested that enough, right, you can make a theory. The theory is chicken fried steak is greasy, right? It's super greasy. But the thing is, though, the reason why a theory is not a law is because there might be some very few exceptions. For example, if you were to put a chicken fried steak into an air fryer instead of putting it into a deep fryer, would it be less greasy? Absolutely. It would have less calories, right? Right? But generally, though, the theory, right, most of the time is correct. Does that make sense? And then we get to scientific law, right? Scientific law is law. It doesn't change, right? For example, we have Newton's laws. We have Newton's laws of motion, or Newton's gravitational law, those kind of things, or Einstein's theory of relativity is actually a theory, but things like that. Oh, here's a good one: Kepler's laws. Kepler's laws tell us that planets that rotate around the sun actually rotate in a elliptical fashion, right? That's Kepler's laws. So those are things that they're so proven right so far that they haven't been disproved. They become law, right? But theory is just one step below that, right? Or one step below that, okay? One step below that. So But there's a lot of theory out there, right, that pretty much are true. So we haven't found anything to disprove those yet either. And I'm sorry, I skipped ahead. But here we go. Here are the definitions for scientific theory and scientific law. You need to know these definitions because they'll probably be on an exam, right? So a theory, tested explanation for a broad segment of basic natural phenomena. So the atomic theory, for example, I'll just tell you now that chemistry hasn't changed in the last 100 years, right? And so here it says the theory is withstanding and has withstood for 200 plus years, more than 100 years, right, for the atomic theory. But again, there's still experimentation to be done. Nothing has disproved it yet. But then we have scientific law. After a series of experiments, a concise statement using words or math describes a fundamental relationship of matter, of nature. For example, we have the law of conservation of mass, right? That's actually one of the laws of thermodynamics, and it says that matter cannot be destroyed or created, right? Matter cannot be destroyed or created. It just gets interconverted into different things. Okay. So that's the difference. You really don't have to write this down. I posted these on notes on Blackboard for you. I literally posted this entire PowerPoint on Blackboard for you. I sent out a message. Did anybody get that? Yeah, I sent out an announcement that said I post my notes on Blackboard. I'm going to record the lectures. All that stuff. I can't remember what else I said. So you can write this if you want to. Feel free. I'll give you time, but it is already written for you. I prefer you write down the examples I give you, right? But I just see a lot of you like staring at the board and doing that kind of thing. Anyway, so okay, how about this? I'm going to move on. But if you want to write it all down, copy it from the Blackboard notes because it's the exact same. I promise. Okay. So how do we measure things? We use our senses, right? We use our senses. Sight, hearing, smell, taste, touch, right? Mostly we use our sight, right? You don't want to smell too many chemicals. It kind of hurts when you do that. Hearing, you can hear things too, but really you're using sight, right? So this is actually a fun part of the class that's about to start here. I was very excited about putting this together. So we're going to talk about sight for a minute. Your first participation question, okay? Go ahead and scan the QR code. Which line is bigger, A or B? Feel free to talk with your friends if you want to. This is why you're in a house. We've got 11 responses so far. Which line is longer? Remember that this is your participation grade right here, so make sure you log an answer. So far I have 19. I need 7 more, or yes. 20? Oh, dang, I forgot to bring a ruler. That's okay. We'll use this thing. Hopefully I don't get in trouble for using this. Okay, 25. Is that everybody? I think that's everybody. 6. Wait, hold on. Hold on. 14, right? Because we have 7 back there, 7 right there, right? And that's 25. Okay, perfect. Okay. Let's see who's right. Oh, I'll show you the responses. See, in the other room, I don't have to do this because the projector has like 2 screens and you can see them at the same time, but not in here. So those are the responses, right? Most of you say that they're equal. A little bit say that their B is bigger, and one says A is bigger. So let's measure. Don't do this, in real life. This is bad, but okay. So from here to here, so is that 2, and that also is that 2. So they're equal in length. Crazy, right? It's an optical illusion. And the reason why it's an optical illusion is because since this one is diagonally longer here, right, and it's shorter here, it makes you think that that one's longer. But if you look at this triangle, it's actually an equilateral triangle. All the sides are the same length. It's crazy, isn't it? Absolutely crazy. So that's a good time. I guess the point of that is that even when you're using your eyes to do scientific research, you can't always believe what you're seeing. Make sense? There's more. Oh, A and B are equal length. All right, let's take a look at this one, okay? There's no question for this one, but we'll just talk about it. Is this guy going up or is he going down? That's the crazy thing about it. Like, he's going down, but then he's going up. How's he still here? It's crazy. It's absolutely crazy. And then if you look over here, look at this one. What's wrong with this? What is wrong with that? Well, I'll tell you right now. This this pin, right? It's not connected to anything. It's crazy, right? And then this is supposed to be coming out at you, closer to you, and this is supposed to be in the back, right? But for some reason, they both look like they're coming out at you. It's absolutely insane, right? Okay, let's do another one, okay? Get your phones out. Another question's coming up. Are these lines horizontal? Sorry, they are horizontal. Are these lines parallel or do they slope? Go ahead and scan the barcode. I'll see what the responses are. So far, we have 9 responses. 14. 20 so far, so 5 more people. 21. 23. 2 more people. I'm so glad your phones work today. There were a couple. Huh? What happened?
It's making login every time, and I try to re-log in, and now it's not taking my code.
Oh, man. At least your first one worked. It's okay. You logged on the first one, though, didn't you?
I got in on the first one, yeah. I keep it on.
No big deal. Okay, so here are the responses. We have most of you saying that they're parallel, some small amount saying neither. That's kind of a crazy answer, though, because if you're not parallel, then you're sloped, right? It's one or the other. So it's kind of a trick question, but that's okay. No big deal. Are they parallel or are they sloped? Turns out that they are actually parallel, right? Which is actually even crazier because even with the orange lines that are there, it still looks like it's sloped to me. I don't know about you guys, but it looks like it's sloped to me still. So, crazy, right? So let's continue on. All right, so this is chemistry. Oh, sorry, this is science, right? And so we will be using units, right, to measure things. And so generally, when we measure things, we have a magnitude, which is how much something is, how big something is, how small something is, and then we have units like inches, centimeters, pounds, things like that, right? Our next section, right, will be about force and motion, Newton's forces and motions, right? And it only requires these 3 things, right? It only requires the length, mass, and time. So keep that in mind. Put a pin in it. That's what we'll be doing a lot of in the next couple of lectures. Not today, though, right? We have standard units, which is a fixed and reproducible value that you can use to take accurate instruments, right? Measurements. But there are 2 systems of units that are in the world. We have the British system and we have the metric system, which is ironic because Even the British have switched over to the metric system. But Americans, we still use the British system, right? So I'm not sure why we're still stuck on, our monarchies, British monarchy system, but we are still using the British system, which is the pounds, inches, miles, while the rest of the world, including Britain, is already switched over to the metric system, okay? But in science class, we'll be using the metric system. Here is an interesting fact that I did not know about. Back in the day, 1 meter, right, was actually based on the length, the distance from the North Pole to the equator. I had no idea that was true, right? And it turns out it was defined as 1/10,000,000th of the distance from the North Pole to the equator, right? It's crazy stuff, right? Just so you know, a meter is longer than a yard, longer by 3.37 inches, right? But interestingly enough, the British standard unit of a foot was actually based on someone's foot. So in Britain, I have no idea whose foot, but it's a very interesting fact. So this is how we actually measured meters back in the day, okay? This is how we measured meters back in the day. But today, the meter is actually based on how much distance light travels in a vacuum, right? That's what we do for today, right? So 1 meter is the distance that light travels in a vacuum in 1/300,000,000th of a second. And if you didn't know that already, this number right here is the speed of light in meters per second, right? 300 million meters per second is the speed of light, okay? So that's the speed of light. So such interesting stuff. All right. Another question. Go ahead. I know I'm keeping you moving. It's late in the day, and I got to keep moving. You got to keep moving too, so we can get through this, right? At least you get to use your phones and receive text messages in between the questions, right? Play a Candy Crush. Kids, do you guys still do that? Play Candy Crush? I'm not that old. I'm barely older than you guys. Oh, I guess I should be really looking at the responses. This is question 3. We have 15 responses so far. $20 people have responded. 21. Sherry, if you're having a problem, log in.
No, I just have to log in every time. It's okay. I mean, I have to put my password and everything in every time, even though I click to stay logged in.
That's so weird. Does everybody else have to do that too? Or are you already staying logged in? That is so weird. All right, one more person. Is it you, Sherry? No, you're done already. Okay, you're done. Okay. All right, we're all in. Okay, so here are the responses. Most everybody say B, right? 5 people said A, and then C, 2 people. So this was in the slide I just talked about, right? Back in the day, they used the distance from North Pole to equator to figure out what the meter was. But in today's time, in modern times, the distance traveled by light in a certain amount of time in a vacuum is actually how we do meter this time. All right. So other interesting stuff that I did not know about, which is crazy because I have a PhD in chemistry, right? The mass, right? Mass is a fundamental unit that remains constant throughout the universe, right? But the kilogram is actually based on a 1.1 meter cube, right? Now that's referenced in Paris. But the interesting thing is this. Here at NIST stands for the National Institute of Science and Technology. They actually have a kilogram weight that they use as a standard for people to weigh things with. So if you have like a dumbbell, right, that's a kilogram, the company that made that dumbbell has to use a standard like one from NIST to make sure that 1 kilogram actually weighs 1 kilogram, right? But the interesting thing is this. That 1 kilogram is not actually even 1 kilogram. It's less than 1 kilogram. It's 0.999999961 kilograms, right? So a little bit less than 1 kilogram. So, and I used to think that all the standards were exactly the weight that they said they were, right? So that's super interesting. But back in the day, it was originally defined as the amount of water in a 0.1 millimeter cube. So a cube that was 0.1 by 0.1 by 0.1 millimeters, right? I mean meters. And that's actually still in reference in Paris right there. Fun stuff. A little bit more about mass though. It used to be called a slug, right? That's where actually slug comes from with like firearms, if you knew that, right? You know, this guy got shot with a lead slug, you know? That's what that comes from. But we don't ever use it anymore. We don't even use it in the firearms world anymore. When I was working cases, I literally stopped working cases back in April, I think it was. No, February was the last case I worked in DFW. And we don't use that word anymore. We don't use the word slug anymore. People hear it on TV a lot, but in real life, we don't use that word. I guess you do use it in shotguns because they have like lead slugs and shotguns, but that's about it. When we're talking about actual bullets and stuff and cartridges, we don't use the word slug anymore. So in America, we use pound, right? In America, we use pound. But the difference here is that I need you to know that mass is something that's the same throughout the universe, right? But when we talk about it in terms of Earth, we call it weight, right? And weight is how much you weigh here on Earth, right? And it has your it has your mass taken into account, right? But it's not the same everywhere. And the reason why it's not the same everywhere is because gravity pulls you down on Earth, okay? Gravity pulls you down on Earth, which are actually theories that say that gravity is actually pushing us down on Earth. But that's something to be talked about in a theoretical physics class, right? And the bigger an object is, the more it pulls you down, right? So Earth is actually the moon is actually 1/6 the size of Earth, right? It's 1/6 the size of the Earth. So what happens then is that on Earth, you weigh 300 pounds, right? But since the moon is much smaller than the Earth, it has less gravity, and you only weigh 50 pounds on the moon. Dang, I wish I could go to the moon. That'd be great. Except that you couldn't breathe unless you were in a suit, and that suit weighs like 300 pounds. So I don't think it really helps that much. So the point is that, you know, when you get to a celestial object like a planet or a moon or something that's smaller than Earth, right, then you weigh less. Does that make sense? Well, let's say you're on a planet that's bigger than Earth, say Jupiter, right? Will you weigh more or less? You weigh more because Jupiter's bigger, so it has bigger gravity. It's much stronger gravity, right? You could probably barely move your legs around because you weigh so much on Jupiter, right? You can't say that with Saturn though, because Saturn's actually made of gas. So you could, but you could say that. No, you couldn't, because Titan is not even as big as Earth. Titan is one of Saturn's moons, and it has like methane lakes. It's really weird because you think of methane as being in your lighter, not in your lighter. No, that's butane. Being in your house for your stove, right? And it's a gas. But on Titan, the pressure is so strong that methane is a liquid. It's really crazy. Got distracted there, sorry. But anyway, so that's the point, right? Keep that in mind for pin that in your head, okay? So let's talk about time then. Okay, so time used to be dependent on the rotation of the Earth, right, being 1 day, okay? Most people probably think it's still that way, right? Where time is dependent on the rotation of the Earth being 1 day. But now, time is based on the oscillation, right, of the cesium atom, right? It's based on the oscillation of the cesium atom. Oscillation just means vibration, right, and it has waves, okay? And so the cesium atom, right, has 9 million, no wait, what is that? Trillion? That's trillion. 9,192,631,770 oscillations in 1 second, right? So in modern times, we define time, or 1 second, right, as being this many basically 9 trillion oscillations coming from the cesium atom, right? But back in the day, though, what did we do? It was based on 1 solar day, right? And so 1 second was 1/86,400th of a day, right? And that was 1 second. Make sense? Right? So, next question. Go ahead. See, there's some classes where you just can't wait to get back to your phone, right? But here you're like, God, I want to just leave my phone alone for a minute. Oh, well, I guess I should be looking at the responses. So this is your next question. Where would you weigh less? The moon, the earth, or neither? They would be the same. Okay, that was question 3, I believe. No, we were on question 3. That was question 4, I think. Yes. Dang, we already have 24 responses. Almost everybody's already in. 99% of you said it was. 99% of you said it was B. So good job. That is correct, right? You would weigh less on the moon. You would weigh less on the moon. So good job. I was going to have you break up into your teams, to your houses, to discuss the situation, but you're already on point with everything, so we don't have to discuss the situation. All right. So let's talk a little bit about the metric system. Okay. Let's talk a little bit about the metric system. So, in the metric system, length is measured in a meter, mass is measured in a kilogram, second is measured for the time, the ampere is measured for electric current, temperature is measured in Kelvin, right? 1 mole of a substance, that's actually a chemical term to tell you how concentrated a solution is of some acid or some chemical, right? And then what 1 mole is the number of those molecules multiplied by Avogadro's number, but you don't have to worry about that right now. And then there's candela, which is the how bright something is, right? How bright something is. And I think candela is almost the same thing as candlelight power, because a lot of times when you buy a flashlight or a spotlight, it says like 1 million candlelight power or something like that. That's like a candela. Does that make sense? Right? So we have 1 kilometer here, which is 1,000 meters. It equals 5,280 feet, right? Or 100 centimeters equals 3 feet or 36 inches, right? And then 1 liter equals 1,000 milliliters, and then 1 quart, though, is 32 ounces or 2 pints, and 1 gallon is 128 ounces. The point of this thing here is to show you that when you have metric system units, everything is in like tens. Like it's always going to be a 0, right? So it's really easy to convert things. Whereas, I mean, I was making some, so there's this Vietnamese dish called bún bò, right? And it's like pho, but it's a lot spicier than pho. And if you've had pho before, which is just a beef noodle soup type of thing that Vietnamese people eat, which is really good. But I was making bún bò the other day, which is like that, but spicier. And bún bò Huế, actually, is how it says. And one of the ingredients is like, you need like a quart or something of something. And I said, and I thought a quart was like 4 cups or something. No, I thought a quart was 8 cups or something like that. I don't even remember what I thought it was. And then it turned out I was wrong, and when we got done with oh my God, it was disgusting. It was absolutely disgusting what I made. And it took like, if you've ever made bún bò before, it takes like hours to make, like hours. So that was a real waste of time right there. You know, had only it been in the metric system, I would have been able to make some good bún bò Huế that day. Anyway, so these are the most common units we use in the metric system, of course. You know, we have milli, right? We have centi, we have kilo, right? Or we have mega, right? So say you start like with 1 meter, right? If you want to do 1 million times 1 meter, that's a mega. You want to do 1,000 times 1 meter, that's a kilo, right? So kilometer, right? And then if you want to do 100th of it, right? Then that's a centimeter, and 1,000th is a millimeter, right? So it's quite easy to convert back and forth, right? Here's your base unit here, whether it be liter, meter, or whatever, and all you have to do is move the decimal point, And when you move the decimal point, you get to bigger units. You don't have to go to like teaspoons to cups to quarts to gallons, right? It's just really a pain, right? So here's looking at some liquid standards, right? Or liters, right? And so a volume of liquid in 0.1 meters cubed, right, which is 10 centimeters at 10 centimeters at 10 centimeters, right, is 1,000 cubic centimeters, which is the same thing as 1 milliliter, right? So I don't know if you've ever been to the hospital or you got your COVID vaccine or something like that, and you looked on the syringe, and on the bottom of the syringe it says CC, right? That CC stands for cubic centimeters, which is the same thing as a milliliter, right? So generally you're getting like, of a vaccine, you'd be getting like 2 or 3 cubic centimeters or 3 milliliters, right? Turns out also that 1 cc is equal to 1 gram, too. You see how easy it is to go back and forth between things in the metric system? Yes, 1 cc is equal to 1 gram of pure water, right? 1 mil is equal to 1 cc, right? But then we got to jump down here to the American system, not even the British system anymore, but it's the American system, where 1 quart equals that many liters, right? And then 1 liter equals that many quarts. Would you rather be up here where everything is like ones and zeros, or down there where you have to have all these smaller, weird, conversions? It's crazy. Scientists are simple people, so that's why we stuck with the metric system. So here's the kilogram, okay? The kilogram equals 2.2 pounds on Earth, okay? 2.2 pounds, right? The amount of water in a 0.1 millimeters cubed, right, is also a kilogram. That's why it says, I say cube too, because it says m to the third right there, right? So 1 metric ton then, right, is 1 cubic meter of water. So that's a metric ton. Not the same as a ton like a when you're talking about like a car, a car is like 3 tons. That's different. That's completely different. I don't even know how many pounds that kind of ton is, by the way. So, let's see here. And then, so these are just all regular conversions going back and forth. You have 100 cubic centimeters, right? It's the same thing as 1 million centimeters cubed right there, right? So remember that 1,000 cubic centimeters equal to 1 liter then, right? And then therefore 1,000 liters is 1 millimeter cube of water, right? So it's super easy to go back and forth with these conversions, and you can always, you don't need the conversion factors for the metric system, but if I ever ask you a question that's converting from metric to American system, then I'll give you the conversions. I'll give you all the conversions. Okay? So here are some of the units that we're going to be using in class this semester, right? We'll do volume stuff, right? That's length cubed, meter cubed, right? Or centimeters cubed, or milliliters kind of thing. We'll do area things. That's the area of something is the length cubed, or the meters, feet cubed. We'll do speed, which is miles per hour or kilometers per hour. We'll also be doing some force stuff too, which is the Newton. The Newton is equal to 1 kilogram times 1 meter per second squared. Joules too, for energy. Watts for power, right? But a very important one that we're going to be doing a lot in your first lab on Monday will be about this, okay? And remember to be dressed appropriately for lab, right? Wear long pants and a shirt and cover your feet completely, okay? The density, the lab is going to be about density, right, that we're doing on Monday. And the density is quite simply the mass of an object divided by its volume. And that equals density, right? So there's some densities here of aluminum. Aluminum, right? Aluminum. Iron there, look, iron is actually more dense than aluminum, okay? More dense than aluminum. So have you ever done this before where, say you have like aluminum foil in an oven and you pull it out and the aluminum doesn't feel that hot, but if you have like a steel pan in the oven and you pull it out and it's freaking hot, why do you think that is? It's because aluminum is a lot less dense than iron is, right? So there's less molecules there of aluminum or atoms of aluminum there to burn you, right? It also has to do with its specific heat, but that specific heat has absolutely everything to do with its density, right? Aluminum is way less dense than iron is, so you put a metal pan into the oven at 400 degrees, you pull it out, there's going to be a lot more iron atoms there that have to cool down, right? So it stays hot for a long time. But if it's an aluminum pan, right, or aluminum foil, it has much less aluminum atoms, so it cools down much faster. The average density for the Earth is 5.5 grams per centimeter cube. That's kind of interesting. So we also have liquid densities too, right? This device right here is called a hydrometer, and it's used to actually determine the density of salt water. So if you have a saltwater fish tank at home, I'm sure you've seen this before, where you put this, this has got lead at the bottom right there, and it's got like millimeters mercury or something like that, or grams per centimeter cube to see what the density is. And you can put it in there, and it floats, and how far it floats tells you what the density is. And that tells you how much salt is in your seawater, your fish tank, right? So pure water, as you can obviously, deduce, has notice everything is based on water, right? Just pure water. Pure water is 1 gram per centimeter cubed, or 1 gram per milliliter. But salt water, though, its density is actually 1.025 grams per milliliter, right? So salt water is much more dense. So a good example of this is when I'm making my saltwater fish tank water, I'll have completely deionized water that's completely pure, and I'll have it in like a 7-gallon bucket. And I can pick it up pretty easy because it's only like 20 pounds, right? But then I added the salt to make it to 1.25. I actually do 1.024 because my fish like it a little bit less salty, but that doesn't matter. If I added the salt, that like 20-pound bucket of water turns into like 40 pounds of water. It's that's the big difference there, right? Urine is 1.05 to 1.03 grams per mil. Why does that change? Why is there a range there for urine? Absolutely. If you're dehydrated, your urine's going to be way more dense, right? The color will be much darker, right? But if you're hydrated and you got tons of water in your system, right, then your urine will be less dense and it will be a lighter color, right? That's how you can tell if you're dehydrated or not, okay? All right, next question. What is more dense, oil or water? Don't worry, these questions will progressively get harder, and then it will require you to speak to your housemates about it to discuss and figure out the right answer. And remember, getting the right answer means that your team will earn more points, and the team with the most points will get the most extra points at the end of the semester. So this is Q. We're in Q3? No, we're not in Q3. Yeah, we're in Q4. There it is. No, we're in Q5 already? Holy mother. Yeah, we're in Q5. All right, only waiting for a couple more people. All right, so everybody's in. Interestingly, it's like half and half. So what I want you to do is talk to your house and convince your housemates of the correct answer. If you think the answer is that oil is more dense, try to convince your housemates that the oil is more dense and tell them why you think that. If you think water is more dense, try to convince your housemates of that. Go ahead, start talking. I'll give you 2 minutes to talk about this, and then you can vote again. Let's see if we can get everybody on the same page. Has everybody done talking already? We can move on. Have you convinced your housemates of the correct answer? Yes? All right, let's see here. All right, scan the QR code again and answer again. Let's see if anybody has the wrong answer. Yes. It's not supposed to make you log in every time if you click on there. Oh, I think the problem may be are you on the school's Wi-Fi? If you're on the school's Wi-Fi, you don't have to log in every time. Yeah. All right, we've only got 19 responses here. 21. Okay, good. Okay, everybody's in. Okay, so I don't know how this happened, but it's the exact same result as last time, which is like half and half. So talk again. Convince your people. I want all the same answers. Convince your people. Okay, that's enough. Let's just talk about this. All right? Whenever you have oil and water, right, what sits at the top? The oil sits at the top, right? So what's the thing that's more dense? It's going to be the water, right? Because the water is heavier than the oil, right? All right. At least nobody put neither. Neither was the trick answer. Okay. So that should clue you in on something, right? If you have it in water, you can tell how dense it is, right? If it's above water, then it's not very dense at all. But if it sinks into the water, like a piece of lead, it's super dense. It makes sense, right? Because everything of density depends on water. Water has 1 in the grams per mil, and everything else is based on that, right? So if you're more dense than water, then your density is going to be 1 gram per mil and higher. If you're less dense than water, you'll be 1 gram per mil or below. Does that make sense? Okay. And if you forget, go home and throw some vegetable oil into the water. Okay? Cook something. All right, so that takes us to what this entire lecture is about. It's about learning how to do conversions, right? And in chemistry, we call this doing dimensional analysis. Okay? We call this doing dimensional analysis. Where did my laser go? In my pocket. Okay. So first thing you have to do, right, is choose a conversion factor. For example, 1 inch equals 2.54 centimeters, or 2.54 centimeters equals 1 inch, right? Then you can arrange your conversion factor so that you can get the right answer, right? And then you calculate it. So I'm going to go ahead and do this for you now. We're going to do a few examples, and that's going to be about it because the class isn't over yet, but I'm being parched. So let's go ahead and get this done. I tell you now that your next test is going to have a lot of conversions on it. So make sure you know how to do a conversion using dimensional analysis. Okay. Let's see here. Oh, sorry. I've got to make sure my pen's working. There we go. Okay. I'm trying to get this thing out the way, and it's not getting out of the way. Previous. There you go. Next. Okay. So the question is, how many centimeters are there in 65 inches? Okay. So the thing you do is you begin with what you have in the question. It's 65 inches. Okay. So you write 65 inches. Okay. Like that. And then you draw a line across like that. And then you say your conversion factor. Okay. Your conversion factor here is 1 inch per 2.54 centimeters. So your the goal here is to cancel out the unit that you don't want. So to cancel something, one has to be above the line and the other has to be below the line. So 1 inch goes here, right? And then 2.54 centimeters goes here, like that, okay? So all you have to do now is cancel out the inches, because the inches are above and below the line, right? You're left with centimeters right there, and the 1 at the bottom of the denominator. So all you have to do then is multiply. So what happens is you multiply across, right? You multiply across, and you divide up and down. But since there's a 1 down here, is there any dividing to be done? No, because anything divided by 1 is that number. So the only thing you're going to be dividing, the only thing you're going to be doing, in this question is multiplying 65 times that. So 65. This is a TI-30, by the way. This is the kind of calculator that you need to use. Okay, if you don't have one like this, it's fine as long as it's not a graphing calculator. So 65 times 2.54 gives you 161. Oops, sorry, 165.1 centimeters. Okay? Yes, ma'am. Say that one more time. We will have rounding rules coming up. We'll have rounding rules coming up. Right now, it's just learning how to do the conversion, right? So any conversion can be done this way. Okay? So let's try another one. How far is 50 kilometers per mile? How fast is 50 kilometers per hour, right, in miles per hour? Okay. So here we have the conversion factor already. 1 kilometer per hour is equal to 0.621 miles per hour, right? And so what do we want to start with? We start with a 50. And the kilometers is at the top, right? And then right here, you can see that there's an H there for hour, right? It's at the bottom, right? Because that's this line right here. When you have that line there, per hour, it means the same thing as divided by, right? And then the other thing too is that it is understood that if there's nothing in front of the unit, it's a 1, which makes sense, right? Because what do we say here? We say 50 kilometers per what? 1 hour. Make sense? Okay. We draw out our line like that. Luckily for us, we don't have to really do anything with the hour because it says to go to miles per hour. So the only thing got to change is the kilometers, right? So you want to get rid of the km, so the km goes at the bottom, right? And the miles go at the top, right? Oh, miles, not meters. Like that, right? And then that 1 kilometer goes down here, right? And then the 0.621 goes up here. Okay? So what are you left with? KMs cancel out. You're left with miles per hour, right? And all you have to do now is what? Multiply 50 times 0.621. Oops, if you could type it in right. Come on, Doctor, no. So that equals, without any rounding, 31.05, not kilometers, miles per hour, right? There will be a lot of conversions. So make sure you know what you're doing with that, right? You always start with the thing that's being asked, right? And your goal is to cancel out the unit of the thing that's being asked. And you do that with a convergence factor. Yes, Sherry.
So I get everything except for how you put that 1 hour on the bottom. So the 50, like, how did you know to put that?
So 2 reasons, right? Whenever there's so like in basic math, when you have something like x, right? And there's nothing in front of the x, you assume it's a 1. That's the first reason why, right? Because if it were not a 1, it would be like 2x, 3x, 4x, something like that. But the other thing too is that when you say this term, kilometers per hour, right? How many hours is that? It's 1 hour because it's kilometers per 1 hour. Just like it's miles per 1 hour. So when you're driving on the road and you're going 60 miles per hour, what that means is that you're driving 60 miles distance and it's going to take you an hour to do that. Does that make sense? Right? That's how I figure out if I have the right amount of gas too. You know, did I do a math problem wrong? What's up? Go ahead. Yeah. Yeah, that's fine. That's fine. Yeah, that's how I actually figure out how long it's going to take me to get somewhere, right? If I'm driving from here to Houston, right, and Houston's like 300 miles away, and I'm going 80 miles per hour, right, it's going to take me like 4 hours to get there. Because 300 miles divided by 80 is like 4. So around 4, right? Does that make sense? It's good times is what that is, driving to Houston. No, not really. I'm kidding. It's not good times. Next one, right? Oh, we just did that. I don't know why I did that. Sorry. Oh, I know why. The only reason why I put this up here is because I want you to know that either one can be used, right? Because this equals that, right? Where 1 kilometer, right, per hour equals this, miles per hour, but also 1 mile per hour equals this many kilometers per hour, right? So you can use either one, right? So how fast is that number right there, which is 50 miles per hour in kilometers, right? So it's not like the other one, right? The other one was 50 kilometers per hour in miles per hour. But this one is going to be 50 miles per hour in kilometers per hour. So let's do that. We start out with our 50 miles per hour. Remember that there's a 1 in front of the hour. I'll put 5, sorry. 50, okay? All right. Do I have to do anything with this hour at all? No, because it's still per 1 hour, right, on both. Okay? So what needs to go at the top then? And what needs to go at the bottom? Right. Who said that? Miles at the bottom, right? So miles goes at the bottom because you want to cancel out miles, and then kilometers goes at the top, right? So you find the one that matches here, right? So you can use either one. You can either use the 1 for that one there to put there, or you can use the 1.6 to put there, because they both say, right, kilometers per hour. But if you're going to use this one right here, you have to use that number for miles per hour, right? If you're going to use that one there, you're going to have to use that number for miles per hour. So let's do it both ways, okay? So 50 miles, 1 hour, okay? It's both the same right now, right? Both are the same, okay? All exactly the same right now. But for the top one, I'm going to use that conversion factor, where the top is going to be 1, right? And the bottom is going to be 0.621. But for this one, I'm going to use that one. So now the top one is going to be 1.61 kilometers to 1 mile. You see that? Both of these mean the same thing, right? So when I do this calculation, I better come out with the same answer, right? Okay? So let's try this. The first one here, of course, miles get canceled. And so you're left with 1 kilometer up here and then 0.621 there. Let me write that clear. I can't even see it myself. 0.621 miles. There we go. And miles get canceled out, right? So we have 50 times 1, right? And then we have 1 times 0.621. Well, we know that you multiply anything by 1, it's the same number again. So really all you're doing now is doing what? 50 divided by that number right there, right? So let's try that. 50 divided by 0.6, oopsies, clear, 50 divided by 0.621. That's about 80.5, right, per hour. Okay, let's do this one now. Here, both of these are 1, so that's 1 times 1, right? So this says 1, but then you have to multiply 50 times 1.61. So 50 times 1.61, oops, not 1. Let me try that. 50 times 1.61, 80.5. The exact same answer. And there's a fly in my face. Excuse me. There we go. Right? So using either conversion, right, you get the same exact answer. You can use either conversion. Does that make sense? Okay. Let's do a couple more before we end the day. 22 inches. So we start out with 22 inches at the top, right? Remember what the conversion is? 1 inch equals 2.54. Is that what it was? Centimeters? I'm pretty sure that's what it is. Hey Siri, how many inches in a centimeter?
1 centimeter is 0.39 inches.
Oh, I said it wrong. It should be the other way. Hey Siri, how many centimeters in an inch?
Here's what I found from AskNumbers.com. 1 inch in is equal to 2.54 centimeters.
Here we go. So, inches goes at the bottom, 1 inch, 2.54 up here, centimeters. Inches cancels out, right? And then you get, oh, I forgot, it's also even going to meters too. So we have to add another conversion. So, one more conversion, right? We want to change centimeters to meters. So every, sorry, there's a fly flying around here. We want centimeters at the bottom. We want meters at the top, right? So that centimeters can cancel. Okay. How many centimeters in a meter? I know, but do you want to ask Siri again, or do you guys know? Hey Siri, how many centimeters in a meter?
1 meter is 100 centimeters.
So you can put that up here. 1 meter over 100 centimeters, right? Siri knows this stuff. You should too, right? Now, centimeters cancels, and you're left with meter there. So literally what you have to do here is multiply 22 times 2.54 and then divide it by 100. Well, I was about to use my phone, but I should really use the calculator. Let's see. 22 times 2.54 divided by 100. That equals 0.055 meters. Which kind of makes sense because remember that 22 inches is almost 2 feet, right? And how many feet are in a yard? 3 feet are in a yard. And a meter is bigger than a yard, right? So that's why you have less than a meter here. About half a meter. Make sense? Right? Any questions? about how we do conversions? I know I did a second step in there, right? But you could go as long as the eye can see with these, right? And just cancel stuff out until you get to the right answer. And just do the math. Multiply everything at the top, multiply everything at the bottom, and then divide them. Okay? That's called dimensional analysis. We do that in chemistry all the time. We still got a few minutes left. Let's try another one. Oh, my God. Okay? How would one express 1st and 10 in meters? Well, 1st and 10 in football is what? How many yards is that? I'm a scientist. I have no idea. I don't watch football. What is 1st and 10? Should I ask Siri? Hey, Siri. What is 1st and 10?
1 over 1 plus 10 is 11.
Oh, that's not helpful. That's not helpful at all, Siri. That's not helpful at all. Oh, you know what I should say? What is 1st and 10 in football? Hey, Siri. What is 1st and 10 in football?
There are 16 NFL games Friday through Sunday. The Colts take on the Lions on Friday at 6 p.m. The Steelers meet the Panthers on Friday at 6:30 p.m. The Eagles take on the Jets on Friday at 6:30 p.m. The Vikings take
Okay, that's enough. If this were Alexa, it works so much better. Okay. So how many yards are in a football field? There's 100 yards in a football field, right? So there are 10 lines, correct? In a football field. And then maybe. Let's try that. Okay, so it's 10 yards, right? Did you look that up, or were you just holding out?
I thought you were kidding. I didn't think you were serious. I didn't know what that meant.
All right. I had to go through and think about it, you know? Oh, man. I got it. Stupid mosquitoes. Nasty. All right, so 10 yards, right? Over 1 yard, right? Cancel out the yards already there. And then 0.914 meters. It's that easy, right? And if you multiply something by 10, all you have to do is move the decimal point, right? So that would be 9.14. Oops. 9.114? No. 9.14. No. What am I saying? Yes. 9.14 meters. God, it's getting so late in the day. Okay. It's that easy, right? Okay. All right. There's only 2 minutes left in class. I don't want to talk about significant figures until next week, so we'll do that next week. For you guys that have lab with me, I'll see you in 15 minutes in the lab. That would be helpful. Any questions?